question?
So,
So the final is gonna be everything except midterm two, right?
I cut a lot of stuff from midterm one also.
Okay.
So like Bernoulli equation isn't explicitly on the final, but then, we also use Bernoulli for like pipe flow.
Mhm.
So you should definitely know it, but I'm not gonna ask you a question.
Is it
purely on
modified
Bernoulli.
on there too, or
Yes.
okay.
Yeah. And even from homework one, the only part of that I'm gonna ask you for is hydrostatic forces on surfaces.
Okay.
So manometry, and buoyancy cut out from the final.
So would you say to study more on homework four then?
Well, homework four is gonna be a big part of the
Big
final
part?
exam. Yeah. Homework four and homework one.
Gotcha.
Good, how are you, Chris?
Right.
Good Father's Day?
Yeah, it was pretty good. Except my son, I didn't see him all day.
Oh,
He's too much on the video games.
oh,
We
man.
barbecued, and I seen him when he had to eat.
Oh, he's at that age. I was like that when I was.
I mean, other than that, we're always together. That's pretty good from all the time. So it's
Good.
basketball, karate, and soccer. He probably gets tired of it because he also has me coaching him. And
I see, I
I
see.
think that's probably the best thing. Getting that time with the coaching.
Yeah, yeah. do something productive together with them, learn skills and stuff like that. That's good.
He's not too much into the modifying car. Right? He does like to modify his bike, but his electric bike
Okay.
wants to go faster. He's a boy.
Oh, that's how boys are.
Yep. We bind parts for that thing, just. We call it CPF. Definitely gonna ride. 13 now.
Oh yeah, he's during his teenage years.
Finding himself quiet. Really talking all the time.
Too cool for dad.
Yeah, because when he was 4 to about 8,
Yeah.
they're just talking nonstop.
Yeah. Everyone kind of goes through that.
Yeah.
So hard growing up.
That's part it is. I came back to school, most of this time growing up, I think, yeah, everything was fun. It is school activity and stuff.
That's good. That's great.
Do that. Oh.
Yeah.
We're too busy. You're working at SpaceX is 60 hours a week and never seen them.
I know work there's crazy. I remember during a time like this was back when I was in college and SpaceX was like the hottest company to work at, but the average age there was like 23. So you know, the only people that could really handle that work schedule are people that were just out of college and don't have any other obligations. But yeah, you can't do 60, 80-hour weeks for like a family and stuff. That's
Their family getting tired, Sundays and days and. So when we go back to school.
Hey, so other thoughts left?
No, I still have, but I only had 120. Some people got a lot when they first got there.
No, yeah.
They're on me.
Yeah, right now that's joining because everyone's joining and everyone's public.
Yeah, it looked a little funny. I'm like, it's got value pretty high. Like, gonna drop. And they did.
That's actually my mother just got a job.
How much did they give him? For my content.
I don't remember, but I think it's value 8,500 or something like that.
Yeah.
And they do something. No, I guess it's first job too, or first big job that are like food and stuff.
I mean, he'll be able to buy into it and stuff. Definitely fun.
Which department were you in?
That was a propulsion. So really very Indian. Also doing inspection.
I think you mentioned that, or they upped his position to CNC and Liber and a little bit of the something. Because I think there was a power change or something in the company, and he's supposed to come in as Liber. And they notified him and like, hey, we're gonna change position to CNC. That doesn't mean like their teacher on the phone.
Like a slaying machine.
Yeah.
They're crazy. Especially the ones with accesses and stuff like that.
Well, too, because he has no experience in like any of that. So like, oh, it's fine. We'll keep him around.
What's that? Yeah, they would pick me up because like, I mean, I came back from my ride. Signing like your was okay.
Would you recommend killing the stocks or
Once he gets to March, he should be able to a lot.
there's a lot of people that you was talking to that was working on it when he did like no tour stuff?
I'm giving back
Yeah,
to
yeah,
Yeah.
like 5 years, something, just sell everything. So like
You can always have it as a retirement fund.
yeah.
You never had it, so you never, That's all I was doing, to just leave it there.
How long do you work?
5 years. It's enough to have another graduation. Beautiful. 2 7.
Second shift or first shift? First shift, first shift. Starts out what?
Easy hours, and I was going from Montana, so I had to wake up at 3:30
Oh,
just to be there by 5.
I don't know why this dumbass chose second
Second
shift.
shift.
Yeah.
I mean, at least
It's
it's
like,
not
oh, it's like-
traffic.
Yeah, I know it complete. But then it's like, oh, well, I can have like two stuff or like a little dollar more than the whole night. I don't know, but it's not really worth it.
Well, my buddy, he always wanted nights. Everyone did.
Yeah.
He might still be there. Talk to him in a while.
I
All right, it's 3 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? So last week that we're gonna have together, so it's like so kind of feels like I just met all of you, and then right after this, you're gonna be gone. All right, so we have our last three, well, I guess technically last 2 lectures this week. So today we're covering something new. I think this should be a very interesting topic for everyone. I think this is generally what people think of when they think of fluids. So it kind of sucks that we have to kind of put it at the very end. There's just so much else to cover beforehand. But today we're covering the concepts of lift and drag, mostly drag. Although probably up until this point in your lives, you probably thought of it as air resistance. And so we're going to just go over it conceptually. Like I said last week, I won't be able to give you a homework with problems on this topic just because the final was already on Thursday. And I'd rather you guys just focus studying on the final exam for the last, couple of days. And so we'll go over, conceptual stuff, because that I at least can ask you questions on the exam. But, there will be no problems associated with this. Now, granted, the examples are in the lecture notes that I posted online. And so if you are interested, you have to check those out. And there's a lot of more information about this in the textbook as well. Just because, I think especially for this campus, I think just a lot of interest for the students that I've kind of seen over the years. If you're looking to get into aerospace, you're looking to get into automotive engineering, this is kind of where fluid mechanics really makes an impact on those fields. Computing drag and seeing how that affects performance. So we'll go over the concepts for that today. Again, just kind of from a conceptual point of view, and then just so that I can ask you some conceptual questions for that on the phone. Okay. Speaking of the final exam, remember that it's going to be 2 days from now. So that is on Thursday, June 25th. Remember, for the final exam, you're going to have twice as long for the final. Not that the exam is twice as long as the midterm, but it's just awkward otherwise. So, and remember, you can bring two 8.5 by 11 sheets, both sides, so twice as much as the two midterms. Okay. To prepare for the final exam, definitely start with the study guide. So that should be posted. That I think has been posted on Canvas since last Thursday. So definitely check that out. And in terms of content, homework 1 is going to, or homework 1 and homework 4 are going to be your best bets for study. Okay. Homework 2, if you recall, was Bernoulli equation. So technically we've been using Bernoulli equation, in other subjects in this class. So we use it for potential flow. We use it for pipe flow, obviously. So you'll be using Bernoulli, but I'm not going to be asking you a question explicitly on Bernoulli. So homework 2 you can probably skip for study for the final. Homework 3 was control volume analysis, which was midterm 2. Which I told you last week I'm not going to ask you that again. I'm not going to test you on that again, just because I just tested you on that last week. Okay. Speaking of midterm 2, I did finish grading those this afternoon, and so I do have them with me today. I forgot to compute the average. It's a little bit tricky to compute the average for this one, just because I have the if you scored better on the second midterm, I swapped that for that higher percentage of your grade. So you should see that already. So if you go on Canvas, you should see that whichever midterm you scored higher in, that is on the 30% category in your grade book, whereas the midterm you scored less in is on the 20%. Okay. Generally speaking, and it's not just this class, just in fluids in general, the midterm on control volumes is always, the scores are always a little bit lower on that one. So I would say the majority of the class, I think, did worse on this one than the first midterm, but that's very typical for this for fluids. So, but one thing I did compute before the start of class today was the overall class average. So with all the midterm scores and the homework scores in right now, basically the class is sitting at about a 75%. So if you recall from the very beginning of the session, what I do after all the grades are in, if that overall class average is below a C plus, I will add points to everyone's grades until the average is there. Okay. Now I usually don't like to report this at this point in the class, just because a lot of things can change with the final exam. Final exam members were at 40%, so a lot of things can still change. But if the class were to end today, you could probably expect maybe 3.5, 4 points to be added to your score right now before I assign points. Okay. But again, things might change with the final. So if everyone does really well in the final, then there's going to be less of a curve, if that makes sense. Okay. All right. And so I think that's a lot of announcements, but I think that's everything that I had to say. Are there any questions I can answer for good? Yes.
So those points, will they be added to?
They'll be added to your overall score at the end.
Okay, so it'd be weighted 100% then?
Exactly.
Okay.
Yeah. Yeah. So you'll see a score on Canvas, but I won't necessarily use that score to determine the final grade, because I'll add to that before yeah. But I can't add it to Canvas just because Canvas doesn't have a way to do that. So what I do is I download all the grades as a spreadsheet, and then I just add to the spreadsheet, and then I use that to determine the final grades. Yeah.
So our final grade is we should look at the Fullerton or transfer.
Exactly. Yeah. Oh, one more thing. So I had a couple people ask me last week about, because the final exam is going to be 3 hours. It's kind of a slog fest. And so a couple of people asked me if we'd be able to take a break during that exam. I thought about it, but it's unfortunately it is a little bit too much of a just to kind of take a break and to kind of let you guys out. It's a little bit too much of a risk, just because things can happen if you're outside the classroom. So we're just going to go straight. But I'm not going to hold you guys prisoner in here. So if you have to go to the restroom, feel free to do that. But you can only be gone for a short period of time. So we're just going to go straight the whole 3 hours. And if you finish early, you can turn it in. But of course, if you need to take a break, you can sit in your chair, I guess, or you can go to the bathroom if you need to. Okay. So I apologize. I know that 3 hours is a long time, but just with the environment and kind of how the department is with this stuff, we kind of just have to go straight. Okay. Okay, all right, so let's go ahead and start the lecture for today, which is external flow over immersed bodies. Okay. So, like I just mentioned a couple minutes ago, this I think for this campus, and I think for a lot of the applications that I see students use fluids for, I'm thinking about like senior design projects, things like Formula SAE, Baja, Rocket, things like that. This is probably the area of fluids that I think gets applied the most. Okay. And of course, in industry, if you're in those fields, and this is kind of what you're thinking about all this time. Okay. So the situation in general is kind of like the following. So we have some kind of object. I've drawn it in the shape of a potato just because the this object can have any shape. But as we'll see, the exact geometry of your object is actually going to play a big role. Okay? And so this object is going to be immersed in some kind of fluid. Right? So generally, the way that we usually describe it, there's some kind of uniform flow that's headed towards the object, just like that. Okay. All right. But this uniform flow has some velocity. So typically we call it something like u infinity. Okay. Right. The reason we call it u infinity is because the infinity symbol is meant to describe the flow conditions far away from the object. So infinity means that it's infinitely far away, but not really, because you can't be infinitely far away. That's just the convention of it. Okay. And so as this flow hits this object, approaches this object, right? The flow is going to interact with the object just because the flow cannot pass through the object, right? And so what's going to happen is the flow is going to hit this, right? Something called a boundary layer is going to form, which we're going to talk about what that means in a second. Okay. And then a wake region is going to form typically as well. Okay. Now, the part that we're interested in, and the part that engineers are typically interested in determining and evaluating, are the forces that develop on this object as a result of its interaction with the flow field. Okay. And as engineers, we're interested in computing and determining what those forces are. Okay. Now, in reality, with a very complex geometrical object, the forces that develop here are actually very, very complex. And realistically speaking, a lot of times you're going to need some kind of computing, maybe like a computational fluid dynamics simulation to determine it. But from a qualitative perspective, usually we break these forces down into two main categories. Or types, I guess you can say. Okay? One of that being a drag force. So drag force is defined as a force that develops within the same direction as the fluid flow. Right, so if we look at that, if we look at our object that's drawn above there, our flow is going from left to right, so a drag force will also go in the left to right direction. Okay. Right, so we can depict a drag force that looks something like that, so F drag. Okay. The other type of force that we're interested in, which admittedly, we're not going to talk too much there, we're going to focus mostly on drag, is a lift force. Now, we discussed lift force a little bit. When we talked about potential flow, we talked about the Magnus effect. We talked about spinning baseballs and things like that. But a lift force is a force that develops in a direction that's perpendicular to the flow. So again, going back to our object up here, technically perpendicular, you can go perpendicular in a lot of different ways. You can go up, down, out of the page, into the page. All of those are considered lift forces, right? But just for the sake of simplicity, we'll draw a lift force in this direction, just like that. Okay. All right, so it seems fairly simple, right? We're just computing two forces, but the nature of these two forces and how they're actually computed is actually quite complicated. Okay. Now, this class of problems here, this class of analysis, we call external flow, because the flow is external to the object that we are considering. Okay. In a lot of ways, people consider external flow to be the opposite of what we covered at the end of last week. So, end of last week, so Wednesday and Thursday, we talked about pipe flow. So pipe flow is what I consider to be internal flow, which is flow that occurs inside of an object. So that's kind of the main distinction that people make between these two. Okay, so when people say external flow, usually they mean flow around the outside of an object. Internal flow is flow that's occurring inside, usually through some closed volume, like a pipe or something like that. Okay. Now, if we had a bit more time, we'd go kind of really deep into the flow characteristics between those two situations because they do actually behave quite differently. Especially with the particular concept that we're going to learn today called the boundary layer. So boundary layer only is really a concept in external flow. Internal flow, the boundary layers kind of merge together. But the flow characteristics are different, even though I would say both internal and external flow, they follow the same equation, they follow the same physical laws. But the way that they develop and the way they interact on the object is quite different. That's why people kind of make this. Okay. But external flows obviously have a lot of applications in engineering, right? So this object, even though I drew it as kind of like a potato shape, you can imagine that to be maybe like a car, airplane, maybe a fish swimming through water, right? You can even look at stationary objects too. So maybe like a building, right? So the flow characteristics of, air that's going around a building, that has a big impact, especially if you're designing like a skyscraper, right? So, external flow has a lot of applications out there, and these concept of drag and lift, are important to know. Okay, but you'll kind of see, probably as we go along in the lecture, I would say external flows have a very strong importance in engineering. So you might be wondering, why did we save it for last, and why does it seem like we're kind of rushing through it? Well, there's only so much we can do with just pencil and paper. A lot of, I would say, the real work in drag and lift, is done computationally at this point, just because of, the complexity of the geometry and the complexity of the flows. But, at the very least, I think, I don't want you guys to leave this class with at least a conceptual understanding of the factors that go into lift and drag and what things can affect their behaviors. Okay, so that's the plan for today. Any questions on this so far? Okay, all right. So let's dive a bit more into it. Okay, so let's go through some general characteristics of external flows and their behavior with certain types of objects. Okay, so let me kind of draw the same object. So the figure up there is going to be a little bit busy. So here's our object. Okay. Again, it's potato shaped. Okay. And just like above, we have some flow field that is hitting. Okay, and then that flow has a speed u infinity. Okay. Now that u infinity, maybe I should have defined this up there. That u infinity actually has a term, a specific term. So oftentimes we call this the free stream velocity. Now we call it the free stream velocity because if that object were not there and basically this velocity field was free of any objects, that's the velocity that it would have. Okay, so that's why we call it the free stream. Okay. And just like I mentioned before, once the flow hits the object, the flow has to essentially go around because the flow cannot pass through the object, right? And so if you look at the streamlines around the object, you'll see that it kind of forms kind of something like this. Where you're going to see on the front end of the object, the part that contacts the flow. Obviously, you have your stagnation point, right? So there's going to be a stagnation point where the flow stops. But what you'll also observe is that there's a very thin layer of fluid that actually goes around the object around the front end. Okay. So this very thin layer, and so it's kind of hard to draw here, but I'll say kind of draw it like this. So that very thin layer is what we call the boundary layer. So it's literally the layer of fluid that forms on the boundary of our solid surface, hence the name boundary layer. Okay. Now that boundary layer has a lot of very interesting characteristics, and it actually is very complex. Boundary layers were studied for a very, very long time in the field of fluid mechanics. It's not as studied nowadays because I would say at this point we understand a lot of the boundary layer, but there's still a lot of very interesting and complex fluid mechanics there. Okay, so that's important to note. The other important to note is this region behind the object, which we call the wake region. Right. So I want to identify these two regions in the external flow because a lot of what is computed what a lot is determined in terms of the drag forces and the lift forces really depend on the behavior of the boundary layer and the size of the wake region. Okay. And so I want you to kind of keep that in mind. And so, before we kind of start diving a bit more into the concepts, I want you guys to have an understanding of what these terms mean. Okay. So the boundary layer, the thin layer of fluid that forms around the object on the upstream side of the object, and the wake region is this kind of low pressure region on the back. Actually, let me write that down instead of it drawn. Boundary layer. So the boundary layer is the thin layer of fluid that forms on the surface of the object on the upstream side, okay? And here, I'm making this distinction between the upstream side and the downstream side. So upstream side is the part of the object where the flow is coming from, right? And the downstream side is the opposite side of that. Okay, so that's the region where the flow is flowing to, right? And then the wake region. So this is the region that forms directly behind the object on the downstream side. Okay. Right, and typically what you see in the wake region is that the flow in that region has very different characteristics than the freeze. So typically, you're going to have very slow kind of circulating flow. And most importantly, for our drag considerations, the wake region is actually going to have very low pressures. Which you'll see. If you've ever seen, if you've ever seen a TV commercial or YouTube commercial for like cruise ship, right? And they have that aerial shot of the cruise ship that is kind of flowing through the ocean, right? There's always a kind of V-shaped region that kind of forms behind the cruise ship. That's essentially your wake. Okay. So the flow characteristics in that region is very different than okay. And in fact, the difference in flow characteristics between the free stream and the wake region are what develop all these drag forces that will run the distance. Okay. Okay. All right. So that's just some definitions. So I want you guys to kind of keep that in mind, as we're going through our discussion today. Any questions on this so far? Okay. All right, let's talk about the object a bit more because the geometry of the object, like I mentioned, is gonna play a pivotal role in terms of its flow characteristics. So generally geometry can be a very complex thing, right? And so even just looking at a human, right? So putting a human in a flow field, the human has a very complex geometry. So to fully characterize a geometry would be very difficult. But for our sakes, I would say we can put geometries into two broad categories. Okay. So the first type of category is what I call a streamlined geometry. So streamlined is kind of the official name for it that we use to discuss it in fluid mechanics. But just conversationally, when people see these types of objects, people usually describe them as very aerodynamic. Okay, which is not a bad descriptor, but maybe not as precise as what we want. Okay, so these objects are usually have a very long shape. They're much longer than they are tall. And the idea is that their shape is meant to contour very closely with the fluid flow that may go over it. And generally what you see from a streamlined body is that it has relatively smooth curvature, okay, which again is meant to kind of mimic the flow lines or the fluid flow lines that go around that object. Okay. Right, so think of objects like an airfoil. Think of objects that like a high performing sports car, right? So these objects are much longer than they are tall because as flow goes over it, the idea is that you'll see once we start talk about drag. The idea is to provide as little disturbance to the flow field as possible. Okay? Right, some examples would be think of like a sports car or an airplane. Right, so these are streamlined type objects where they're much longer and they want to produce as little drag as possible. Okay. The other type of body, which I would say is or the other type of geometry that I would say most objects tend to fall into this category is what I call a blunt. So a blunt body, is kind of everything else, but it's these are objects that are taller than they are usually long. Right. And so what you also see from these types of geometries is that there's sharp corners and edges. And so unlike the smooth contours of a streamlined body, okay? And so a blunt body, we call it such because they, are usually designed without consideration of the flow. And so these are going to provide a lot of disturbance to the flow field as it flows around. All right, and you'd be surprised, so there are some objects where their performance strongly depends on its drag characteristics, but has a very blunt body. So think of like a Jeep, right? So think of a car that's much taller than it is wide, or taller than it is long. Excuse me. So a Jeep is not a very aerodynamic vehicle, partly because it's not designed to be. Jeeps are designed for more rugged kind of off-roading stuff. But you're gonna eat kind of a lot of performance or a lot of efficiency just by it having a lot of drag on it. Okay. Okay, so those are kind of the two main characteristic or two main types of geometries that we are going to consider. And technically, both of these types of geometries here, they're going to be subjected to the same boundary layer, wake region, drag forces. But the idea is that streamlined bodies are going to experience much more drag. Okay. I guess another way you can say blunt bodies are expected to experience much more drift. Right, which I think matches intuitively. I think with what people understand. Okay? So if you drive like a Lamborghini down, you just floor it, right? You're expected to be able to reach much higher speeds than if you try to take your Jeep and you try to floor it as well. right? Now, part of that is because of the engine, right? So Lamborghinis have a much more powerful engine that's designed for speed. But another big aspect of that is the geometry of the vehicles. So because of the kind of the shape of the Lamborghini, right, it's able to kind of cut through the air with as little drag resistance as possible. Okay. Okay. Any questions on this so far? Okay. All right. So for this first section of class, we're just defining stuff, and so we've kind of gone over the definitions of the boundary layer and the wake region. We've gone over the definitions of the geometry. A few more definitions before we actually start to apply the stuff. Okay. Okay. So let's go ahead and define the types of forces that get produced a bit more specific. All right, so I know I've already kind of mentioned the lift force. I've already kind of mentioned the drag force. Lift and drag are, I would say, what we consider to be the overall effect of all of the forces that get put on, right? So it's kind of easy to think about things as a single drag force or a single lift force, but in reality, the forces that act on the object are actually very complex. They're very complex. There's a lot of a lot of factors that go into it. So when I say these forces, these are kind of more, I would say, more fundamental forces rather than just the overall lift and drag forces. Okay, so there's two types of forces to know. So one being the wall shear stress. Okay, so the wall shear stress, this is going to be the main effect of our viscosity, right? So viscosity is a concept that has come up quite a bit in this class. So we know viscosity is basically our fluid friction. Okay, so as a fluid kind of flows past an object, because of viscosity, the fluid basically tries to take an object with it, right? So if you rub your two hands together, there's friction there, and so that friction kind of drags one hand along with you. Okay. Right, and so just like friction forces typically do, friction forces act parallel to the body surface. Okay. Okay, so if I were to draw it, right, so even on a streamlined body, so you're going to have some wall shear stress, right? So you draw kind of like a teardrop kind of shape, just like this, right? Yeah, low that's kind of going through it. So because of viscosity, there's going to be a shear stress that develops along the surface of the body. And it goes just like this. Okay. Now I bring up the wall shear stress just because I think, if you kind of have just like kind of a basic understanding of fluid mechanics, you would think that the wall shear stress is something that's typically significant, but it's actually not. And so I would say for most external flows, the wall shear stress is pretty negligible. So most of the time you just don't even feel it. And it's not because that it's not there. So the wall shear stress is there. It's just that usually the other force just is just so much greater that it kind of dwarfs everything else. Okay. There are situations where the wall shear stress is relevant. And I think we'll probably have enough time for me to just kind of mention that at the end. But just know that the wall shear stress is not the dominant force that gets acted on these situations. Okay. Which is strange because I think if you were to stand as a human if you were to stand in kind of a flow field, right, you just kind of stand outside when they're standing in a wind, you kind of feel it, right, so you kind of stick your arm out, you kind of feel the wind kind of flowing past it, so you would think that the wall shear stress is what's actually pulling you back, but it's actually not, and so it's kind of more of a minor thing. Most of the forces actually come from pressure forces. Now, pressure, remember, is a concept that we've, again, gone over a lot in this class, starting from the very beginning. So remember, pressure is a force that acts perpendicular to a surface. Right? And pressure forces develop just because pressure is just a very natural, it's one of the variables that gets solved for in fluids, right? So just by being immersed in a fluid, there's going to be pressure forces, whether it's fluid or not. Right? Remember, even standing in this room, sitting in this room, technically we're being exposed to atmospheric pressure. We just don't feel it just because we're always at atmospheric pressure. Okay. Okay, so we have our object again, just like this. Okay. So there's flow going at it, although, for pressure's case, there doesn't necessarily have to be flow. Pressure, it still develops in a static fluid, right? But, pressure forces are acting perpendicular to the object, just like this. Okay. So most of the time, when you're computing drag on an object, unless you're in a kind of a very, very specific scenario like before, your pressure forces are going to dominate your lift and drag forces. Right. So kind of as we kind of, develop our discussion for lift and drag, just remember that pressure is going to be the main contributor. Okay. And you might be wondering why, because, if you look at this figure that I drew here, right, it kind of looks like the size of the arrows are the same around the entire object, right? So that doesn't happen in reality. So in reality, because of the interaction of the object with the flow field, the pressure distribution around the object is actually very uneven. Okay. So what that means that around our object, there's going to be regions of high pressure, there's going to be regions of low pressure, okay? And that imbalance of pressure, right, is going to create a net force. And so if you have a higher pressure on one end and a lower pressure on another end, that's going to create a force, in the direction from the high pressure to the low pressure. Okay. So a big part of, analyzing external flow is identifying where the regions of high pressure are, where the regions of low pressure are, really understanding what causes those regions of high and low pressure, and then using that to, compute things like lift and drag. Okay. So the pressure is kind of going to be a big part of our discussion. And so, just kind of keep that in mind kind of moving forward as well. Okay. But I did want to kind of mention at least that, while viscous shear stress is there, but maybe not as important. Okay. Actually, for the most part, you'll see that we're going to consider the flow to be inviscid, but viscosity does play a very, very key role in terms of how the boundary layer develops and how the weight region is. So, even though for, I would say 99.9% of external flow viscosity is not important, that 0.1% actually plays a huge role in terms of what actually occurs. All right, any questions on this? Okay, all right. So last thing I want to go over, before we actually, just stop with the definitions. I know there's a lot of definitions today. Is to talk about the Reynolds number and turbulence. So just like pipe flow, right? We have concepts of laminar and turbulent flow. Okay. Right, and I would say this kind of the same qualitative understanding of what laminar flow looks like, what turbulent flow looks like, that applies here as well. Okay, so laminar flow typically is much more, much more orderly. Has kind of the flow kind of follows these straight lines, whereas turbulent flow is characterized by more chaotic motions and craziness. Okay. So the way we determine laminar or turbulent flow is exactly the same in pipe flow. So we're going to compute the Reynolds number. So Reynolds number has a very similar definition, but there is one key difference for external flow. Okay. Okay, so for the Reynolds number, we're going to compute it. We're going to take the density of the fluid. We're going to multiply that by the free stream velocity, U infinity. Okay. We're going to multiply by some length scale L, which I'll go over in a second, a bit more, divided by the viscosity. Okay. Okay. And then just like internal flow, there are different thresholds for turbulence versus laminar. But you want to be careful. The thresholds for external flow are different than pipe flow. Okay, so generally speaking, if the Reynolds number is less than 2 times 10 to the fifth, right? This generally means that your flow is going to be laminar. If your external flow is between, if your Reynolds number, is between 2 times 10 to the fifth and 3 times 10 to the sixth, that is transitional flow. And then of course, if Reynolds number is greater than 3 times 10 to the sixth, this is turbulent. Okay. Now these are much higher thresholds, right? So if you recall from last week, for pipe flow, our Reynolds number only needed to be above 4,000 to be considered turbulent. This is much, much higher, right? So just kind of keep that in mind. Reynolds number is a great predictor for laminar or turbulence, but hopefully this tells you that the exact Reynolds number threshold is kind of situation dependent. So it changes for different flow situations, different flow geometries. So you want to be careful about that. So if you're determining whether a flow is laminar or turbulent, make sure you look up the thresholds for your specific situation. Okay. And if you're looking at a situation that may not, be one of the traditional kind of scenarios. So let's say you're determining whether the flow is laminar or turbulent over a sports car, right? So, I don't think, Reynolds, back in the day, in the 1700s knew what a sports car was. And so he didn't determine the thresholds for that. But you can probably come up with a geometry that's somewhat close to what you're looking at. Okay. So these thresholds in particular are for flow over a flat plate. Okay. Okay. All right. So same concept. The only thing that's different are the thresholds. The other thing that's different is this L here. Okay. Now this L that we're using for external flow is what's known as the characteristic length. Now, when we computed Reynolds number for pipe flow, there was kind of no question about what the characteristic length was in that situation, because there's really only one length scale, which is the diameter. Okay. Now, for external flow, you have to be careful about what you choose for the the characteristic length. Because you actually do have some freedom, right? And it's actually up for debate sometimes, when you have complex geometry, what you even choose for that characteristic length. Okay. Generally speaking, you want to pick, I would say, for all situations that I've ever seen in my life, I would say 95% of the time that characteristic length is going to be the length of your object in the flow direction. It's a characteristic twice. Okay. All right, so you have to kind of identify which direction your flow is going to be in, and then you measure that L to be whatever the length of your object is in that direction. Okay. But there are situations where you don't pick that length, right? So there are some situations, especially if lift is going to be a big factor in your geometry. Say you're designing an airfoil, you probably pick a different length, characteristic length. Okay. Okay. All right, so that's a lot of definition. Part of the reason why we had to do a lot of definitions is that I kind of did things a little bit in this class a little bit out of order. So we're kind of defining some things here for the first time, but but in reality, there was some stuff that comes before this, notably the Navier-Stokes equations. But because we didn't see that in this class, we kind of had to define all these things from scratch. Okay, any questions on this before we actually get to more study? Okay, all right, so let's talk about kind of how forces actually develop. And a large part of that is through what's called boundary layer separation. Okay. So boundary layer separation is this is a phenomenon that occurs in every object that's in an external flow, right? It's almost physically impossible to get a boundary layer to stick to your object completely. It's just that the degree of boundary layer separation is going to be different depending on the geometry that you have. Okay, but the nature of the boundary layer separation is a big determinant in terms of how we compute drag and lift forces. Okay, so what do I mean by boundary layer separation? So let's draw our object again. Every time I draw this potato, it gets a little bit more circular. All right, so we have our object, we have our flow coming in. Okay. All right, so like we just kind of finished talking about, right? So as the flow kind of hits the object, and as the flow is kind of forced to go around the object, there is a thin layer of fluid that kind of forms around that surface, right? And so around the front end and a little bit of the top and bottom as well, right? There is this thin layer of fluid, which we call the boundary layer. Okay. Okay. Now, the reason the boundary layer forms is that there has to be a region, between the object and the free stream where the flow kind of transitions. Okay. Because, and this is a concept that, is talked about in Navier-Stokes. When a fluid flow flows past an object, if you were to look at the fluid particles that are right next to the object, you'll actually see that they are at rest. Okay. And so the solid object basically imposes something called a no-slip condition. Okay. So for the fluid particles that directly contact an object right at its surface, it's because the fluid is not allowed to slip past that object, partly because of viscosity, right? Remember, I told you viscosity is going to play a very key role, right? So because of viscosity, the fluid cannot slip past it. Okay. All right. So if I were to kind of zoom in, right? So let's say this is our object right here. So the fluid, and I literally mean like microscopically, the fluid particles that directly touch the surface, and only for those particles that directly contact it, those particles have zero velocity. But as you move away from the surface, right, the fluid can then start to have velocity because they're not forced to be stuck to the solid. Okay. But, if you think about, far away from the object, right, far away from the object, we have the free stream. Okay. So between the solid surface and the free stream, there has to be kind of this, I call it kind of transition zone, where the fluid velocity kind of slowly changes from zero up to the free stream, right? That's the purpose of the boundary layer. And so what you'll see in the boundary layer, right, and this is just a rough approximation, the exact profile, again, I told you is a big subject of research, right? But generally speaking, in the boundary layer, your velocity is going to slowly change. Right? Your velocity is going to slowly change from zero at the surface to the free stream at the top of the boundary. So I think that's to me, I think that's kind of the simplest and kind of most straightforward definition of the boundary layer and the reason it forms. Is that, because of viscosity, there has to be this kind of smooth transition. Just because you can't have a discontinuous jump from zero velocity at the surface to all of a sudden free stream velocity, because that kind of violates some principles of conservation. So there has to be some kind of smooth transition, and the boundary layer provides kind of that region. Okay. So for the first, I would say first part of the object on the upstream side, on the front, there's this kind of boundary layer transition region that forms, okay? Now that boundary layer persists, right? So if you kind of go around the object, that boundary layer kind of sticks around, okay? But at a certain point, there's going to be a part where we say the boundary layer separates from the object, okay? Right, and so this location, right, and so and a lot of times, if you really look very closely at the flow field around an object, the location of boundary layer separation is usually pretty clear. It's actually pretty cool to see. Okay, so in blue right here, I've marked the region, so we call this boundary layer separation. Okay. Basically, what you're going to see is that it actually does take some energy for the fluid to maintain the boundary layer. And once you kind of get to the back of the object, the fluid kind of just runs out of kinetic energy essentially. And so once there's not enough kinetic energy to maintain the boundary layer, it kind of breaks and separates from the object, right? And where that boundary layer separates, that's where the wake region is created. Okay. So this idea of boundary layer separation is a very key contributor to drag force, because where the boundary layer separates, how long the boundary layer can stay attached to the object, and the size of the wake region, these are kind of the main determinants of the amount of drag force that an object experiences. All right, so I'm gonna be mentioning the boundary layer a lot, and so just from now on, I'm gonna refer to the boundary layer as BL. Okay, so BL stands for boundary layer. Okay. All right, and so we'll talk about some factors. So I've already kind of mentioned it a bit about the kinetic energy and the momentum, but we'll kind of put some figures and we'll have a stronger understanding in a second. But before we get to that, are there any questions on this so far? Okay. All right. So to kind of better understand why the boundary layer separates, we actually have to go back to our unit on potential flow. Right, specifically, we're going to look at our flow around a cylinder, right? So that was the combination of a uniform flow and a duct. Okay. We have our cylinder here. We have our fluid flow, right? Infinity. Okay. Now, if you recall, and if you recall, we kind of went through this a little bit quickly back then, just because of the constraints of time. But let me just kind of remind you kind of the key points here, right? So remember, for potential flow, what we can do is that we can form a stream function for this flow by combining the stream functions of a uniform flow and a doublet. Okay. From that stream function, we can obtain the velocities, right? And then we can use the velocities together with Bernoulli equation to obtain the pressure distribution. Right, so remember the steps typically for potential flow, this is kind of a very, also very nice, quick kind of review for the final exam as well, because you will see potential flow in the final. Right, so step one for any potential flow problem is to form the stream function, usually as a combination of our building block flows, so uniform flow, outlet, source, sink, things like that, okay? Okay, so from the stream function, you can take derivatives to obtain the velocity components, okay? And then from the velocity components, you can take their magnitude to obtain the speed or velocity magnitude. Okay. And you can take that velocity magnitude, plug it into Bernoulli equation to get pressure. Okay. So we did this in detail for the half body. So I definitely recommend kind of reviewing that for the final. But for our purposes here, for external flow, let's focus on that last step, which is the pressure distribution. Okay. Okay. Right. And so what we found for flow around a cylinder was a very interesting result, if you recall. Okay. And so if we plot it, right, so on the vertical axis, we have pressure. And then on the horizontal axis, you can consider kind of the arc length around the cylinder. So we're basically going to be progressing from the front of the cylinder to the back, right? What we found was an interesting result, right? So what we found was that as we kind of went around the cylinder, right? So the pressure started high. Then as we got to the top of the cylinder, we reached a low pressure. Then as we got towards the back end, our pressure fully recovers, right? So up here, this is the front of the cylinder. Right down here is the top of the cylinder, or I guess the bottom as well. And then by the time we reach the back, the pressure is fully recovered. Okay. All right, and so what we found, right? So what we found was that the pressure on the cylinder was the same on the front and the back. Which was odd, right? And so, what we said back then was that if you experience the same pressure on the front and back, then you experience no drag forces, right? And so now that we're kind of talking about drag forces today, there's a little bit more context in that statement, right? And so, in order for you to experience drag force, there has to be an uneven distribution of pressure, okay? And that's exactly what occurs, right? And so what we talked about back then was that in reality, right? In reality, you do experience a drag force, or generally speaking, unless you're literally the shape of a piece of paper, right? So a realistic pressure distribution looks like the following, right? So on the front end, right? So on the front end, our pressure distribution actually looks the same, but then as you get to the back, right? There's going to be a point where the pressure can no longer kind of climb that hill, and our pressure just kind of flatlines. Okay? Right, so this is typically what so in blue here, this is kind of typically what you see. Okay. So you see kind of a lower pressure on the back end compared to the front end. Okay. All right, so that point, so that location where the pressure starts to deviate from the potential flow solution, right? So we can identify that point right here. Right? So up until that point, right? So up until that point, our realistic pressure is basically the same as the potential flow solution. But right when it starts to break, this is the location of the boundary layer separation. Right? So if we kind of connect this back to our original figure in this section, right? So what we said was that there's going to be a certain point where the boundary layer, this kind of transition region between the solid surface and the free stream, there's going to be a point where that separates from the object and your wake region forms. Okay. So that point right there correlates exactly with where our ideal or where our pressure distribution deviates from the potential flow solution. Okay. Okay. And the reason it starts to deviate there is because, just like, if you think about yourself, right? So if you were to kind of push a wagon, right? Pushing a wagon downhill, I mean, assuming that the wagon's not going to crash into anything, pushing a wagon downhill is very easy, right? You could argue it requires no work because the wagon just flows naturally down that hill, okay? When fluid is flowing from high pressure to low pressure, that's very easy work. That's naturally kind of what a fluid wants to do. So on this front end, when the pressure is going from high to low, a fluid likes to do this. A fluid will do this naturally. So whenever you have an object in external flow, you never see boundary layer separation on the upstream side, just because it's kind of impossible for that to happen, just because the fluid is working on what's called a favorable pressure gradient. Right? So working from high to low pressure, very easy for a fluid to do. Right? But on the back end, right? So once you kind of reach past the top of the cylinder, right? We're now working against an adverse pressure gradient where the fluid is trying to flow from low pressure to high pressure. Which it can do, right? It can do for a small amount of time, right? And theoretically, if you think about it, right? If you think about, think back to your physics class, right? If you have a marble, right, and you float and you roll a marble down a hill, it can technically roll back up the same hill, right? Granted that there's no losses from friction, right? And so if you have a perfectly smooth surface, there's no friction, you roll a marble down a hill, right? It can roll back up to the same height because that's how much potential energy it started with, right? And so that's essentially what the potential flow solution predicts is that your fluid comes in with a certain amount of momentum and velocity coming in, right? Without any losses, without any viscosity, it should be able to recover that exact same amount of basically potential energy. Okay. But real flow is not like that, right? So real flow has viscosity. And what do we know about viscosity and flowing fluid? Viscosity is going to dissipate energy, is going to sap kinetic energy away from that flow. And it's especially more difficult in the boundary layer because viscous dissipation in the boundary layer is actually more enhanced than normal flow as well. Okay. So even on the front end, viscosity is sapping energy from the flow. It just doesn't run out of energy until it reaches the vacuum. And so essentially, once the flow kind of runs out of kinetic energy, that's when the boundary layer will separate from your object. Okay, good. Now, where a boundary layer will separate from an object is kind of an intense, I would say, subject of engineering interest, right? In fact, a lot of times, if you're going to be working in aerospace, you're going to be working in automotive, and you're in charge of designing the chassis. You're in charge of designing the outer geometry, right? A lot of times, you're going to be engineering or designing your device to delay boundary separation as much as possible, because the longer your boundary layer can stay attached to your object, the smaller your wake region is going to be. That means the less drag that you're going to experience. So to minimize drag, right? So generally, you want your boundary layer to stay attached for as long as possible, because the longer it stays attached, that creates a smaller wake region. Okay. So I'm going to box that just because that's going to be kind of an important concept, right? So again, we're not really going to do any calculations for this. This is actually not something we actually can do calculations for because boundary layer separation. When you talk about it, in concept like this, I think it's a good concept to learn. But the details of actually working with it and predicting where the boundary layer will separate is actually very complicated, and you do need software for that for the most part. Right? Generally speaking, it's good to kind of talk about what factors go into it, right? Because connecting this back to our discussion before on geometries, right? The reason streamlined geometries have the geometries that they do is that streamlined geometries will, they're designed so that they delay boundary layer separation as much as possible. Whereas blunt objects, you're going to have boundary layer separation very quickly, very easily, and that creates a very large wake. Okay. So last thing I'll kind of cover here before we go to break and before I return your exams is just kind of visually kind of the difference between a streamlined versus a blunt body in terms of their boundary layer separation. Okay, so a streamlined object, typically looks like this, right? Right, so a streamlined object will have kind of this very long kind of shape, right? And you can see that it has another characteristic of a streamlined body is that the cross-sectional area kind of tapers near the end, so you have kind of a very small, kind of thin tail, right? The reason for that is that if you look at the boundary layer, because of the smooth contours, the boundary layer kind of stays attached for almost the entirety of the whole body, right? And even though you do have some separation, just because the boundary just has to separate at the end, there's just no way for the flow has to move forward in some way, right? But you have a very, very small wake region because that boundary layer stays attached for pretty much as long as it could. should have put an almost there because it's, unless you have creeping flow, it's kind of impossible to get the boundary layer to stay attached for the entire body. But you can get it so that it's practically attached almost completely, 99% to the bottom. Okay? Versus a blunt body. A blunt body, so if we draw just kind of a block here. All right, so a block is kind of your characteristic blunt body because it has sharp corners, it's not streamlined, it's just kind of this big block, right? Right, so here you have a very early boundary layer separation. Part of that is due to the profile of this object. Another part is due to the sharp corner, right? So there's basically no way, right? So if you look at the sharp corner here, there's no way for the boundary layer to make it around that sharp corner there. It kind of has to separate at that sharp corner. Okay. But because of the early boundary layer separation, you have this ginormous wake region that forms on the back. You have a very large low pressure region that forms on the back of your object. Hence, you have a ton of drag because of the pressure differences, right? So you have much higher pressures on the front, very low pressures on the back. That creates a net force in that flow. Okay. All right. Any questions on this before we take a break? Okay. All right. So let's take a break till 4:30. I have your exams here. I brought all the midterm ones as well. So if you haven't picked up your midterm ones, we'll pick it up as well. So there's a small pile of midterm one, a big pile of midterm two. Okay. You guys can come up and get it, and then we'll resume the lecture at 4:30. All right, it's 4:30, so let's get back into it. So if you're on Zoom, I'll bring the exams tomorrow. I can bring the exams on the final exam day as well. So if you haven't had a chance to pick up your midterm exams, I keep it in my office. I'm contractually obligated to keep the exams in my office for a year. But I very quickly, if you ever come to a few of you have come to my office, but you'll see that I've exams that are kind of piling up massively. So it does. I don't want to keep them, so please pick up your exam just to kind of help limit the clutter in my office. And plus, it's good for you to kind of see as well. So yeah, please come pick up. At the very least, you can pick them up on the final exam day. Okay, all right. So let's get back into talking about drag. Okay, so right before the break, we talked about this idea of boundary layer separation and the wake region, where what we compute as drag, or what really determines drag, is really kind of determined by how long you can keep the boundary layer attached to your objects. Okay. Okay. Now, before we get into actual, computations of drag, I do want to add a caveat here. Okay. So, for the most part, geometry is going to play the biggest role in your determination or the amount of drag that your object experiences. Okay. So that's the number one factor, okay? And of course, it's a lot more nuanced. It's a lot more complex than just saying that this body is streamlined, this body is blunt. Although I'd say that's generally enough just to get the conversation started. But generally speaking, you want to geometry is complex, right? And so there's no, there's very few engineering systems or engineering devices or vehicles of interest that are very simple geometry, right? Even your most basic ass car, right, that's driving on the road, I don't think you would consider any of those to be a simple geometry, right? Not at least not one that you can compute using kind of simple pencil and paper calculation. Okay. But the geometry is going to be the most important factor and the most complicated for sure. Okay. There is another factor that does determine or does help keep a boundary layer attached, and believe it or not, it's turbulence. Now, I kind of skipped this section in the notes just because I want to make sure I get some lift before the end of today. Just because, tomorrow is mostly going to be review. We're going to talk about Navier-Stokes a little bit, but I want to finish all the lift and drag stuff today. So I did skip a big section on boundary layer in the notes. But one thing I talked about in that section was turbulence and its effect on boundary layers. Okay. Now, believe it or not, turbulence actually helps a lot, actually. Okay. So generally speaking, if you have a turbulent boundary layer, so let's say you're in a regime where your Reynolds number is greater than 3 times 10 to the 6, or whatever the threshold is for turbulence for your specific geometry, right? If you can achieve turbulence, that actually helps keep your boundary layer attached for longer than normal. Okay. Now, the reason for that, and this unfortunately is a big theme for today. The reason for that is a little bit beyond the scope of this class. But I would say generally speaking, you can think of, because of the chaotic and because of all the random motion that's associated with turbulence, that kind of naturally adds a lot more. How should I say? It adds kind of a lot more kind of passive energy, a lot more kinetic energy to the flow compared to laminar flow. Kind of the simplest way I think to think about it, right? Because what we kind of just discussed is that the boundary layer, once it kind of runs out of kinetic energy and it can't basically progress through that adverse pressure gradient, that's when the boundary layer separates. But if you were to add some additional kinetic energy to that flow in the form of turbulence, right? Then the flow can kind of progress up through that adverse pressure gradient for a little bit longer. So it's actually very, very interesting. And so, there are actually some situations, right? So what can happen very interestingly. So if you have a very, very streamlined body, right? What tends to happen in those situations is that the flow tends to be laminar kind of throughout the entire part. Which is good in some ways. It's good in the fact that it's easy to analyze, but because the flow is laminar over that streamlined body, then the boundary layer may separate sooner than what you would like. Right. So in those situations, it's actually beneficial to kind of artificially trip turbulence or artificially produce turbulence by adding like a trip wire or maybe like a rough surface somewhere on the surface to kind of make turbulence artificially occur. But you don't want to disturb the flow too much, right? So if your trip wire kind of disturbs the flow too much, then that itself saps too much energy from the flow. So you want to kind of disturb the flow enough to produce turbulence, but not too much so that you're taking the energy away. It's a very fine balance, and the intricacies of that is something that honestly it's not something that I've researched or I have I can claim a lot of expertise in, but it is a technique that I know is used. Okay. And so turbulence is interesting, and if this class kind of interests you and you kind of want to pursue fluid mechanics more, especially at the graduate level, these are the kinds of concepts and kind of things that you'll learn, right? There's a lot to turbulence. Turbulence, I think a lot of people kind of think of as a bad thing because it's generally the thing that makes your plane ride more uncomfortable, makes you spill your Coca-Cola all over your lap on bad turbulence. But turbulence actually does add a lot of good things to your flow. And you'll see, in the next class that you take after this, which is heat transfer, a lot of times you actually desire turbulence because turbulence will actually enhance your heat transfer a lot just because of all the mixing that occurs in turbulence. So, yeah, so don't, try not to have negative connotations with turbulence because turbulence does help with a lot of kind of what we do in engineering. It makes analysis very difficult. And so I can't say that we understand turbulence really well, but it does have a lot of net positive effects on the systems that we use. Okay, all right. So with that said, let's go ahead and move on. Okay, let's move on to what I call let's call this drag computations. Okay. So the section that we just finished about boundary layer separation and wake region formation, that's kind of I guess the reason that drag occurs on these kinds of objects, right? But now the question is, how do we actually work with drag? How do we actually compute it for these types of objects? Because understanding why it happens, at least on a qualitative level, is very different than actually working with it on a quantitative level and incorporating that into your design. Okay? And so I still stand by my statement from earlier that in reality, it's very difficult to get exact computations, exact kind of analysis of drag, just because geometry and flow conditions in these scenarios can be very complex. Okay. So, if after this, after you graduate from here, you end up working for like an automotive manufacturer, you work for Boeing, something like that, right? You'll see that all of their teams there that are dedicated to computing lift and drag, they're using software, right? There are experimental techniques that you can use to compute drag, but like we've already discussed in this class, there's limitations to how much you can do that. But there's so you kind of have to use software on these situations, okay? But a lot of times, when you're kind of first designing an object, or you're just kind of doing, there are still benefits to doing pencil and paper calculations. We still want to be able to get a sense of how much drag is in a system. Okay, and so to do that, we are going to introduce this idea of a drag coefficient. Okay, so the drag coefficient, you can think of it conceptually kind of the same way that we use things like the loss coefficient and the friction factor from pipe flow, right? So if you recall from last week, pipe flow already is already kind of complicated because it depends on a lot of factors, right? And so if we want to compute things like the pressure drop, right, we utilize a tool like the Moody chart, which is kind of like the culmination of a bunch of different experiments that have been run on different pipes, okay? Same thing for the loss coefficient, right? So when you have a 90-degree turn, we have a pretty good idea in terms of how much kinetic based on our tests and experiments that have been done in the past, okay? Now, computation of drag are the same way, right? And so, drag has been of interest, of engineering interest, scientific interest for a very, very long time, right? And before the age of kind of modern computing, these are kind of the techniques that scientists and engineers use to compute. Okay. Okay. All right. So the drag force on an object, we can typically approximate it using the following calculation. Okay. We take 1/2 times the density times the free stream velocity squared. Okay. Right. So you hopefully should recognize that as the kinetic energy term. That's not a coincidence. Okay. We're going to multiply this by what's called the frontal area, right, which I will define in a second. But the most important part of this is going to be the addition, or I guess the multiplication of a coefficient that I'm going to call CD. Okay. Where CD, this is defined as the drag coefficient. Okay. So if you want to find out how much drag force that an object is going to experience, you can see here that it is a function of the velocity. Okay, so the higher your flow or the higher your velocity, the more drag that you're going to experience. That's pretty typical, right? You're going to take basically the kinetic energy of the flow you're going to multiply it by the frontal area, and then you're going to multiply it by this tabulated drag coefficient, okay? Now this drag coefficient, the value of the drag coefficient will change depending on the geometry of interest. Okay. So what the drag coefficient is for a particular object, you can look this up in data tables. There's quite a few in the textbook actually. So if you look at chapter 9 of the textbook, there's quite a few tables that show this. But I think kind of the easier way is to kind of just like most things in where you can even look up data is to look this up on from Google. Okay. So there are data tables that exist for drag coefficients for different geometries. Okay. So what people did in the past to compute drag is that they've run tons and tons of experiments on different objects, and they've computed these drag coefficients based on the forces that the object experiences. Okay, and just like we talked about in dimensional analysis, they then took those results, they non-dimensionalized it, and they kind of put it in a form that other people can use for their own analysis. So that's the idea. And so if you want to compute drag coefficient or you want to compute drag forces on a particular object, let's say that you're interested in the drag forces that your car is experiencing when you're driving down the freeway, right? You would look up the drag coefficient for your car, or at least a geometry that's close to your car, right? Look up its drag coefficient, plug in all the numbers there, and then that will give you an approximate number for the drag force that you're experiencing. Okay. Okay. Now let's also define this frontal area, because this one's a bit interesting as well. Now this frontal area is it's a surface area essentially, right? But it's only the surface area that's exposed to the flow. Right? So the way that is typically defined is that if you're kind of looking in the direction of the flow, right? And you see kind of the projection of the object in that direction, that's defined as the frontal area. Right, so it's literally kind of the area or the surface area of the front of the object that you kind of see from the flow. So it's not the total surface area, right? It's not that. It's just kind of the projected area that you kind of see. Okay. Okay. All right. So that's kind of the simplest. Computing drag, at least based on the limitations for this class, is a lot easier, I think, than kind of understanding the concepts that kind of go into it. Okay. Okay. Which again, the main kind of determinant for that drag coefficient is the geometry. Okay. So different geometries that have more streamlining versus blunt body objects. Streamlined objects are going to have a lower drag coefficient, and blunt objects are going to have a higher drag coefficient. Okay. Any questions on that? Okay. All right. So let's do a quick example. This is not going to be a heavy example by any means. This is kind of more of a thought example. Okay. Let's kind of talk about the concept of a terminal speed. in particular, the terminal speed of a falling object. Okay. Now, so I think most everyone is familiar with the concept of air resistance, right? And so if you think back to your basic physics mechanics class, right? Whenever you did kind of kinematics, you talked about kind of trajectory of projectiles, right? You were always told to ignore air resistance, right? So what does air resistance actually do to an object? Let's talk about that here. Okay. Now, in the absence of air resistance, or in other words, in the absence of drag, when you drop an object from a particular height, right, because of the action of gravity, right, you're expected to basically continue accelerating, until technically you can reach the speed of light if you kind of keep accelerating, right? Right, but we know that doesn't happen, right? So if you ever go skydiving, which if you ever do, tell me how it is, because that is something I will never do. I am so scared of heights. Right? You know that if you go skydiving, eventually you reach a point where your speed kind of plateaus, right? You're gonna be accelerating a lot, but eventually because of air resistance, your speed will kind of reach what's called your terminal speed. And you no longer will accelerate, you just kind of hurtle towards the earth at a constant, very high speed, but your speed kind of caps out. Okay, so to demonstrate this, let's consider a fairly kind of simple object. So let's consider a spherical piece of hay. Okay, so we have our piece of hail. It's approximately a sphere. So let's say the diameter of this hail is 1.5 inches. I thought about just doing this conceptually, but I think it actually helps to put some numbers on this just so that you get some idea. Okay. Again, I'm not going to expect you guys to do a problem like this on the exam just because there's just no time to do a homework assignment on this. But this example here is just to kind of hopefully help kind of illustrate kind of a lot of the concepts that we talked. Okay, so let's say that this piece of hail is falling from the sky, right? So it falls out of a cloud just because that's what hail does. It comes down and it dents your windshield. Right, so as the hail is falling down, there's essentially going to be a fluid, right? Or at least kind of what the hail experiences. There's going to be a rush of air or a velocity field of air that's kind of flowing past it. Okay. Okay, and so that air is going to have a velocity u infinity. Okay. And so what we're interested in computing is what is the terminal speed of this piece of hay? Okay. So as this piece of hail is falling from the sky, right, it's going to be subjected to essentially two forces that are acting on it, right? On the one hand, you have its weight, right? So the weight of the piece of hail is dragging it down towards the surface of the earth, right? So that's going to be a force in the negative y direction, right? But since our flow here is going upwards, it's also going to experience a drag force in the upwards direction. So terminal speed, right? Terminal speed you can consider as a state of motion where there's no net forces, right? Because there's no longer any acceleration, right? And so when your two forces here are going to perfectly cancel out, so when the drag force equals to the weight, that's when you're going to reach your terminal speed and your hail is no longer going to accelerate. All right, so essentially, so we can draw a free body diagram here, although it's going to be fairly straightforward, right? So essentially, we're going to reach a sum of forces where the weight is going to be equal to the drag force. Okay, so all we have to do is just kind of plug in everything here, and you're going to see that there's going to be one unknown left for us to solve for the fluid velocity. Okay, so let's start with the weight. Right? So the weight, we know how to compute this, right? So hopefully you know how to compute weight before this class. But weight is simply the volume of the object multiplied by the density of the ice multiplied by the acceleration due to gravity. All right, so granted that we know the density of ice, and so ice is essentially water. Technically, so ice is very interesting. So because of the way the crystal structures form in ice, the density of ice is actually slightly less than the density of water. That's why when you put ice cubes in your water, the ice tends to float. So kind of an interesting thing. I'm surprised I didn't mention that when we talk about balloons. Okay. So the density of ice we know it's like 980 kilograms per meter cubed, and the volume we can compute based on the diameter. Okay. The drag force, right? So for the drag force, we can plug in our formula that we have up here. Okay. Because even though for most objects, it's going to be hard to determine the drag coefficient, a sphere is something that has been studied a lot. And so we can actually get a pretty good idea of the drag force based on its tabulated drag coefficient. Okay, so the drag force is going to be 1/2 times the density. Now you have to be careful here, right? Because the density that you're going to plug in for the drag force is the density of the flowing fluid. Okay. Which in this case, it's for this particular example, it's a little bit confusing because we have ice, or ice is essentially frozen water. But when you're computing the drag force, remember the fluid that's actually moving past the piece of hail is actually air. Okay? So this is going to be density of the air multiplied by the terminal velocity squared. So that's what we're going to be solving for. Okay? Multiplied by the frontal area, multiplied by the drag coefficient. Okay. All right, so again, so everything in here is pretty straightforward, except let's plug in for the frontal area. Okay. Remember, the frontal area is not specifically the surface area of the object, it's the area that's projected that basically the flow is going to see. Okay. And so for a sphere, right? So if you were the fluid, right? So let's say that you're kind of looking upwards, you're underneath the hail, maybe hopefully, you won't look at it too long, but the hail is just going to poke you in the eye, right? But what you see, assuming that you have no depth perception, is that you see a circle, right? So the frontal area or sphere is a circle. Okay. Right, because that's the area that's basically projected from the sphere. You can think of it as like the object's shadow. I think that might be a better way to think. Okay. So A front, if we take the area of a circle, which we've done, probably close to 50 times this class, right? It's pi over 4 times the diameter squared. Okay. And we are given diameter in the problem, right? And so that is not a problem for us to compute. Okay. Next thing we need is the drag coefficient. Now, again, this is one that's tabulated, but it is one that you might have to do a little bit of work in computing. Okay. Right. And so if you were to look up a particular figure or a particular table for the drag coefficients, you're going to see that it not only depends on the geometry, but it also depends on the Reynolds number as well. Okay. So you are going to have to do a little bit of computation, right? So you do have to kind of know what the Reynolds number is. But for this particular example, for a sphere is very closely studied. Okay, so if we look this up, so back when I wrote these notes back in 2019, this was figure 9.21. I don't know if it's that same figure in the textbook. But what we find in that situation is that the drag coefficient is about 0.5. Okay. And so we plug kind of everything in, right? And we solve for u infinity. Right? So we plug everything in. U infinity is going to be equal to the square root of 2 times the volume of our piece of hail times the density of the ice times gravity divided by rho density of the air times the frontal area times the drag coefficient. Squared there. Okay. All right, so we have everything here on the right-hand side, right? You can compute the volume of a sphere. Volume of the sphere is 4/3 pi r cubed. So we plug in the diameter for that, we get something different. But anyway, we have everything here, and then what we get is the terminal speed is 91.2 feet per second. Which is cool, right? So I think this is the first time I think that a lot of people have kind of computed, what the terminal speed actually is. For the most part, most of the time we ignore air resistance, so it's really cool to kind of see this for the first time. But on the other hand, this is still extremely fast. And so every second that hail is traveling 91 feet, which is about 30 yards. So about a third of a football field, this piece of hail is traveling every second. And all that just to come down and crack your windshield. So yeah, this hail has a vendetta against your 2015 Canon. Not speaking from experience at all. All right, any questions on that? Okay. All right. So again, so calculation like this, again, not going to be on the final exam, but I did want to do something just to kind of help illustrate these concepts, right? So, what we learned from this example here is, first of all, how to use this drag coefficient formula, right? This is kind of the most naive, the simplest way to compute drag, which again, if you're doing kind of precise engineering work, you're probably not using this formula here. But, at the very least, this formula is perfectly fine for you to start your calculations, okay? So, if you were curious about, what's the drag forces that your car experiences as it's driving down the freeway, you could very easily use this formula here. The difficult thing, of course, would be to compute the drag coefficient, which you'd have to look up online, which, there are a lot of resources for that nowadays as well. Okay. Okay, so for the last 45 minutes today, I did want to talk a little bit about lift. Okay. So I would say, for the most part, drag has more, I would say, engineering interests overall in the fact that there's more applications where drag is important. But lift is also extremely important, especially if you're going to be in automotive and aerospace engineering fields. Right? Okay. But let's recall kind of the definition for lift, right? So generally, I think when you hear lift, you think of forces that lift an object off of the ground, but that's not necessarily what lift forces are more general than that, right? So lift forces specifically are just any forces that develop in the direction that's perpendicular to the flow. Right. So as long as the force is being produced in a direction that's not in the flow direction, that's essentially your lift. Okay. Okay, so just like the drag force, the pressure is going to play a pivotal role here, right? So in order to generate a lift force, you have to have an asymmetric distribution of pressure around your object. Okay? Whereas for drag forces, we are considering the differences in pressure on the front or the back and the back side of the object. For lift, we're looking at the differences in pressure either on top or bottom or, in directions that are perpendicular to the flow. Right? Now to generate lift, right? And I should say, so just like drag, where pressure kind of is the main determinant or what causes the lift force, right? Just like in drag, the way that we get asymmetric differences in pressure is through the geometry. Okay? So geometry again is going to be the biggest determinant of the lift force. Turbulence does play a role in the lift force, just like in drag, um, but geometry is going to be the number one determinant of the force as well. Okay. With that said, right? So with that saying that the geometry is most important, in order to generate a lift force, you have to have an asymmetric geometry, right? Because that asymmetric geometry is going to create asymmetric pressure distributions. Okay. So you cannot have a lift force if your object is symmetric across an axis of the flow. Yeah. All right. So the object that I've kind of been kind of using a lot for the streamline bodies, as in something that kind of looks like this. So it has this kind of teardrop shape, right? Right. You might look at this and you might think that, maybe this is the cross section of an airfoil, but a shape like this would actually be terrible at generating lift, right? Because if we look at the flow direction, right, so we have flow that's actually coming towards the object just like this. And if we were to draw a line of symmetry in that flow direction, right, so let's say that we kind of draw a dotted line here. That kind of separates your geometry into top and bottom halves. You should see that the top and bottom halves here are basically mirror images of each other. So we basically have a symmetric object across that axis. And so because we have a symmetric geometry, there should be no lift, if anything, very little lift that's generated on this object. Okay. Because with a symmetric geometry, that means our pressure distribution is going to be the same on top and bottom. And if you don't have a difference in pressure between the two sides of your object, then there's no lift that can get generated. Okay, so you have to have some asymmetry in your object. Okay. Okay, so a typical airfoil. Okay, a typical airfoil, it kind of has that same teardrop shape, but you would see that there's kind of a hump that kind of makes it so that you don't have symmetric geometry all through that. Okay, so it looks something like this, and I'm notoriously terrible at drawing these airfoils. Okay, but it makes it so that the top is kind of humped just like that. Okay, so that's not bad, but kind of terrible at the same time too. All right, and so if you were to draw the same line, right? So if you were to draw a line that kind of splits it in two, just like that, right? Right, you can see that we have actually very different geometries on the top compared to the bottom. So a geometry like this is much more likely to generate heat. Okay. Okay, good. All right, so then how do we compute lift, right? So just like in drag, right? Because we're often working with very complex geometries in these cases. Most practical situations, again, you're going to rely on computation, you're going to rely on simulations to compute this, right? But just like in drag, there are tabulated results that we can take advantage of. Especially if you're only looking for approximate calculations. So just like there's a concept of a drag coefficient, there's also a concept of a lift coefficient as well. Okay. So there's a very similar formula for the lift force that we can kind of compute here. Okay? So the lift force is equal to, right? So just like the drag force, we start with our kinetic energy. So we start with 1/2 rho squared. Okay. We multiply by an area. Okay. Now this area is not the same area as our drag force coefficient. right? So this area is known as the planform area. So that's another concept that I'll describe in a second. Okay. But most importantly here, we're going to multiply this whole thing by CL, which is what we call our lift coefficient. Okay. Which again, like the drag coefficient, this is something that's tabular. Okay. So let's talk about the planform area. This one's kind of interesting. And every time I see this, I always think that I make a typo in my notes. So it looks like platform, but it's not platform, it's planform area. Okay. So the idea with this planform area is kind of the same as the drag, the frontal area for the drag coefficient, right? So the reason we use the frontal area for the drag coefficient, you can think of that as the area in which the pressure distribution is acting on, right? So for drag, right, the drag is generated based on a pressure difference between the front and back sides of the object, right? And so the net force that's being acted upon, right, is basically a product of the pressure that's on the front end multiplied by the frontal area. Okay. For lift, we have the same concept, right? So for lift is basically generated as a difference in pressure, but the areas that it's acting on is a bit different. Okay. Instead of acting on the front of the object, right? The lift is being acted on either by the top or bottom, right? Depending on if we have positive lift or negative lift. Okay? So think of this planform area as the approximate area on which the pressure is acting on. All right. So admittedly, this can get a little bit complicated, especially for, the applications that typically use lift, which are, aerospace applications. So the computation of the planform area kind of has a very simplified form. So a planform equal to, okay, it's going to be the product of two lengths as most areas are, okay? So it's going to be the product of the length of the object that goes into the page, okay? Because usually when you're drawing figures for lift, you're drawing just a cross section of that object, right? But typically that object has depth that goes into the page, okay? So however long you expect your object to extend into the page, that's the length that you multiply by, okay? And you're going to multiply that by what's called the chord length. Now, the chord length has a very specific definition. It's a term that's used in wing design in general, or just airship design in general. So the chord length specifically, and this is used using wing terminology. Chord length is the distance between the leading edge and the trailing edge of your object. So essentially, the planform area is a rectangular area. So essentially we're computing a rectangle, right? Where the lengths are kind of you can consider them approximate lengths for your object. Okay. So you have the length or the depth in which your object goes into the page. You have just the simple chord length from the leading edge to the trailing edge of your object. So that rectangular area, we take that as kind of the approximate area on which the lift forces are acting on, right? And we use that to compute the total lift force. Okay. All right. So besides kind of that kind of nuance there with the planform area, the way we compute lift forces by hand is very similar to how we compute the drag forces. Okay. So the tricky part, believe it or not, the tricky part is actually obtaining the lift coefficient. But then once you have the lift coefficient, you typically have everything else that's in the problem, or they're very easy to determine. And you can compute the lift force. Okay. Okay. All right. Any questions on this so far? Okay. All right. So I think last concept, and I think we'll probably end early today, is this concept of angle of attack and stall. Okay. All right. So what we know is that lift, well, from the 15 minutes that we've been talking about, and lift is basically generated based on an asymmetry of geometries. Okay. Right. So one just, very qualitative, very dirty kind of way to compute lift is, to draw kind of the cross section of your object, cross section of your wing, draw a line that's in the direction of the flow, and see how asymmetric your object is, right? The more asymmetric it is, generally the more lift that you can expect. All right, so one tactic that we haven't really gone over is the fact that a lot of times your object is not static in the flow field, right? So it's not, you're usually not in a situation where once the flow starts, you're kind of stuck that way, right? You can adjust yourself. You can adjust your object to kind of have different kind of lift and drag characteristics. Okay. Right? You actually see this in movies as well, right? And so if you ever watch like a superhero movie, right, there might be a scene where like like a person's kind of falling from the sky, right? Right. So let's say they're kind of falling in this direction and kind of kind of spread out, kind of just like this, right? If for some reason they want to go faster, right? Or I guess you might, if you play Fortnite, you kind of see this every day when you play, right? If you ever want to go faster, right? What's typically done is that the person kind of changes their orientation, right? Where they're kind of going like this instead, right? And then once you kind of turn your body like that, then you go faster towards the ground, right? So that's not just a Hollywood thing. That's not just a video game thing. That actually happens. Because if you think about it, when you're in this orientation, right, you have less frontal area, so your drag forces are kind of more minimized in this state. Okay. Yep, exactly too. Yeah. So if you dive underwater, so the most kind of efficient way to kind of dive deep underwater is to kind of take that orientation, right? So you can't really dive underwater by kind of spreading yourself out just because the drag forces and would be kind of too strong, right? So if you want to go dive deep underwater, you would kind of make yourself kind of as slender as possible within the direction of flow. That way you minimize drag to make it easier to go down. Okay. Okay. So the same can be said about lift as well, right? But, I think the easiest way to kind of illustrate this is by altering your angle of attack. Right? Okay. So I know what I said earlier is that this geometry here can't generate any lift, right? Because it's symmetric. Right? So if we took this geometry here, we kind of draw a line through it, it's symmetric, there's no lift. Right? But what if we took this geometry and what if we kind of lifted it upwards a little bit at a certain angle? Right? So we took the same geometry, but we lifted it up like this, right? Now we still have flow coming at it like this, right? So the flow direction hasn't changed. So the flow is still perfectly horizontal, but because we've kind of lifted it up a little bit, we've changed the symmetry of our situation, right? Because now if we draw a line, right, we draw a line that goes through it. Now we have a situation where our object is asymmetric or not symmetric. Okay. So in this situation, just by tilting yourself upwards a little bit, right, you alter kind of the nature of the flow that goes around it. You break that symmetry, and you can generate kind of more lift in this situation. Okay. So just intuitively, right? So if you ever kind of, you've been to Disneyland, you kind of fly the ship, right? If you want to kind of go upwards on an airplane, you kind of pull kind of the steering wheel back to kind of tilt yourself upwards. Okay. So that again, that's not a Hollywood thing, although it's of course embellished and simplified for Hollywood, but this is kind of what actually happens in reality as well. Right. The way
You'll actually see it on a plane too, if you look up. So you can see the flaps.
Oh yeah, yeah. I was going to get to flaps in a second too. So yeah, so that's exactly the purpose of the flaps too, is to kind of alter that symmetry so that you can generate more lift situations too. Yeah, great point. So the way we quantify this is through this angle of attack. So the angle of attack is this angle that the object makes with the flow direction.
Most people do it too out of a car, they'll put their hand up.
Oh yeah. No, that's a great point as well. Yeah, so generally speaking, the greater your angle of attack, the more lift that you can experience, right? And so when your plane is taking off, you want to maximize that lift force, right? You try to kind of maximize that angle of attack. But there's a limit, right? And so you can't just keep increasing angle of attack infinitely, because something bad will happen, right? Which, for those of you who are familiar with flying airplanes or have experience in the aerospace field, we know this as stall. So what is stall, right? So stall is kind of what we call a situation where you kind of catastrophically lose all kind of lift forces. And it's very difficult, if not almost impossible, to kind of get it back. Right? So you want to avoid stall at all costs if you're flying it. So what happens when stall occurs? Right? So the reason stall occurs is on the one hand, as you increase angle of attack, you are increasing the asymmetry of your wing of your object, right? That's good for generating lift. On the other hand, you're also making your object more blunt. All right, so I'm going to draw an exaggerated situation just to kind of illustrate this, but typically you don't get an angle of attack this high. But let's say that your angle of attack kind of progressed, so that your wing is kind of upwards like this. Okay, so this is like an angle of attack of 45 degrees, which is kind of crazy, right? And so your flow is still coming this way. Right? And just like we kind of discussed earlier, right? A boundary layer is going to form around the object. But what happens when stall occurs is that, if you make your object too blunt and your boundary layer does not have enough energy to reach all the way to the end of the wing, right? What happens is that you have early boundary layer separation, just like the blunt object that we talked about before. So what happens when you stall is that you have this massive wake region that forms behind your wing, which you didn't have before, right? So your wing is mostly designed to be a streamlined object. And so the wake region is very small, if not almost non-existent, okay? But if you increase your angle of attack too much, such that you create this huge wake region, all of a sudden you have a massive amount of drag that you didn't have before. And then from there, kind of a catastrophic kind of cascade of events occurs, which is very difficult to recover from. Okay, because if you have a massive spike in drag force, right, that's going to impede your forward progress, and so that's going to decrease your fluid velocity that's coming in. Right, because the drag force is going to impede your flow. Okay, and then if you have a massive drop in your airspeed, right, that's also going to cause a massive drop in your lift force. Because both the drag force and the lift force depend strongly on that flow velocity, right? So let me go ahead and write out the equation for the lift force one more time. So the lift force is 1/2 rho u infinity squared multiplied by the frontal area, or excuse me, the planform area, multiplied by the lift coefficient. Okay. But the key contributor here is the u, right? And so if your airplane or if your aircraft is massively slowing down because of this drag force, then all of a sudden your lift force is going to fall off a cliff as well. Okay. And that lift force was necessary because that lift force was what was counteracting the weight of your aircraft. Okay. Now all of a sudden, if you have a massive reduction in lift, now you have a net force pulling your aircraft down toward the ground because your weight is just so much higher. Not that the weight's higher, the weight is just overpowering any lift that you're generating. Okay. And then, probably you can kind of figure out what happens from there, right? So if you're not able to recover, if you're not able to kind of recover your lift force, then there's no place to go for your aircraft and just down towards the ground. And that's how crashes occur. Okay. So stall obviously is not a good thing. You never want to stall your aircraft. Okay. And that's if you ever learn how to fly an airplane, that's one thing you learn to avoid at all costs. Okay. Um, altering your angle of attack is still a good technique. You still need to know how to do it because you need to do it to generate lift in some situations, but you can't go too far, otherwise you're going to stall based on this series of events here. Okay. All right, any questions on stall? Okay, a couple minor points kind of before we end today. Okay, so just as Chris mentioned, right? So there's besides altering your angle of attack, there are other ways that modern aircraft can do other techniques that they can do to alter the asymmetry of wing. So one of which being the flaps on a wing. So if you've ever been on an airplane and you've kind of had the privilege of having a seat that's over the wing, right? Or maybe next time you're on an airplane and you're able to kind of see over the wing, right? Look and see what the wing flaps are doing at different stages of the aircraft's travel, right? So look and see what the wing flaps are doing when takeoff. Look and see what happens when the aircraft is trying to land. Look and see what it's trying to do in turbulence when it's trying to balance itself under turbulent flow, right? So that's kind of one way that an aircraft can kind of make kind of micro adjustments to the lift that helps these aircrafts tremendously. Okay. All right. So another note I'll make is that in most situations lift is desirable, right? A lot of times you're designing your engineering device or your engineering vehicle specifically to generate lift. Okay. So that's especially true for aircraft because that's how an aircraft works. The only reason it can get into the air is by generating lift. Okay. But you'll be surprised that there's actually a lot of other applications from lift as well. Okay. So one of which is in automotive, right? So generally speaking, when you think of a car, right, a car only just goes forward, right? But there's actually I would say a lot of good reasons to actually generate lift forces actually in the direction that may be opposite of what you might be thinking. It's actually generally useful for a lift to actually go in the opposite direction, right? To kind of push your car back towards the ground. So the reason for that is that sometimes your car might benefit from that because a lot of maneuvers that your car may want to do, basically whenever you're steering the steering wheel, or just anything that your tires will benefit from a downward force, because the more downward force that's applied to your car, the more control your tires and the traction that you have will get to do. Okay. And so if you look at a lot of high performance cars, not all of them, of course, but a lot of them have a spoiler, which is kind of attachment on the back. Part of that spoiler is to kind of alter the airflow to help generate either lift or negative lift, depending on some situation. Okay. And that was actually very interesting as well. So unfortunately, he no longer works here, but we had a faculty member here. His name is Dr. Mayral. So that was actually a big area of his research, was to kind of do simulations to find out what factors and kind of contribute to kind of the lift on certain vehicles for better traction. Okay. All right. And then you guys know about baseball studios, because we've already kind of talked about that as well. But that's another application for lift. All right. Any questions on this before we wrap it up for today? Okay. All right. So I think for the first time ever, we ended early. So kind of making up time for going over last time. So thank you guys for coming today. So tomorrow we have kind of a weird class session. I do want to have a kind of a half lecture on Navier-Stokes, just because I don't want you guys to leave this class without seeing Navier-Stokes. So the first half will be on that. I'm not going to test you on Navier-Stokes for the final, but I just want you guys to see it. Then for the second half of class tomorrow, we will have a review session for the final. So we'll choose both. Yeah. All right, so thank you guys for coming today. I hope you guys have a good rest of your afternoon. I will see you guys tomorrow.
Thank you, Professor.
Oh, thanks. Yeah.
One problem we had this year was we didn't know how much to do. Yeah. So when I come completely for everything available.
Yeah.
Yeah. But is there a better way to find that angle rather than testing it like?
Yeah, it's always complicated just because every geometry is going to be different. And so, there's tables and there's data out there, obviously, for certain aircraft, but the exact geometry that they're using is different than what
Should
you're
always be based on the plane.
Exactly. I mean, you can find approximate ones, and that's usually going to be your starting point. And so try to find a table of lift coefficient which is close to what they're doing. But it's going to depend on the speed, the Reynolds number, the behind things like that. So, I would say, what's out there in terms of data will get you close. But for that specific aircraft, you're going to have to tinker with. Because the way they do it in practice is that they're going to run simulations on it. I think the aero team wants to go in that direction, but it does take a while to kind of set that up in a way that's useful. So I think for now, probably the most practical thing would be to have a mechanism for variable angle attack and just kind of tinker with it.
Because I was thinking either doing a sliding mechanism where it changes as you push it in and out, or just swapping out plates stuff. Because I think they gave me 10 degrees of freedom, so I can work from 10 to 0. So I just swap out plates, or you just slide it in and out.
Gotcha.
So I don't know which one was better.
Okay.
Yeah.
Yeah, I mean, usually, probably. So, I mean, the other thing for aircraft is you want to minimize the weight as much as possible too. And so, yeah, probably, whichever thing probably has the least amount of weight. Yeah.
At the beginning of class, you mentioned that we should stay homework 1, but is the entirety of homework 1 going to make its way onto the final?
No. So if you look at the study guide, the main thing from homework 1 is going to be the hydrostatic forces on surfaces.
Okay.
So basically, when you have a surface that's underwater, how much force is being generated on it.
Yeah.
That's the only part. So manometry, buoyancy are not going to be on the final.
Okay.
Yeah. Randy, what's up?
So I was just gonna ask, so for the final, as far as material we covered today, it's mostly conceptual.
Yes. Yeah. So because I'm not going to get a chance to give you guys a homework on this.
Yeah.
So I don't feel comfortable asking you to do a problem solving question on something you didn't get to practice. But conceptually, I think, you should kind of understand what we talked about today. So I'm going to ask you a conceptual question on the exam based on this, but yeah, no problem.
But it's more of like a word response, like the one.
Exactly.
Okay.
Exactly.
Okay.
Yeah.
yeah, I was just wondering, I was like, oh shoot, I was looking over the study guide, I'm like, so as far as like reading my questions, some more towards the last one.
Exactly.
Okay.
Yeah. It's gonna be the majority of homework 4, but yeah, just like I was telling him that, you know, hydrostatic forces and surfaces, you can expect a problem from them.
And from homework like 2 or 3.
Nothing from homework 3. So
Okay.
homework 3 was all control volume. So I just
Right.
tested you guys on that last Thursday.
Yeah.
So I don't see the point in testing you on that twice in a row.
Okay.
Homework 2 was Bernoulli's equation, which we still use. So
Right.
Bernoulli's equation is used in like potential flow. It's used in pipe flow. But I'm not going to ask you a question just on Bernoulli's. It'll be incorporated into another.
Okay. Okay, so for, I'm just trying to make sure that I got it.
Sure.
Like,
Yeah.
Pass this next one.
Yeah.
Okay. All right, sounds good.
Yeah.
Thank you.
Yep.
Oh, also, sorry, one last thing.
Yep.
So I got full credit on the first 2 homeworks.
Yep.
I did half of the last one, and then I finished it like today. Do I bother upload doing it or just
For
hold on
homework
to it?
homework 3.
Homework 4, the one that was just you.
Oh yeah. So homework 4 I think was just due on Sunday. So
Yeah.
So for my late policy, it's like dock 10% off per day that it's late.
But
So
I mean,
yeah,
if it dropped, because on the syllabus system you just drop.
I do drop the lowest one.
Should I
Yeah.
just hold on to it then, or should I still upload it?
I think you should still upload it.
Okay.
It just, if anything, you know, I still look through. I mostly just check for completion.
Okay.
You know, but if I do notice anything, I do leave some comments sometimes too.
Okay.
So.
Also on that one, I think it was like number 3, the one with aneurysm question.
Mhm.
Like the part A where what up? Part A, it's asking like the one where you have to do all the dimensions and
Yeah.
everything. That one was like kind of confusing for me. Should I focus a lot more on that one? Do you think that would make its way onto the exam? Or
The
just,
mental
like,
analysis will be a big part of the exam. So
Okay.
I would definitely. I did post solutions for homework 4
yeah.
too. So I would definitely check that out.
Okay. All right. Sounds good. Thank you for answering all my questions.
Yep.